Hi everyone, and welcome to Lab 4. In this lab, we will go over stability and the PD control design for our cube servo position. Okay, in the first exercise, we will analyze the stability of the position and velocity responses of the servo motor. In order to understand the stability, maybe it is best to look at the behavior of an unstable system first. When a system is unstable, for finite inputs to the system, the output of the system blows up to infinity. An unstable behavior is not desirable and could result in physical damage to the hardware or the surrounding environment. This is why the first rule when designing a controller is to make sure that the system will be stable. Next, we have the definition for BIBO, or bounded input, bounded output stability. A system is said to be BIBO stable if and only if, for a bounded input signal, the output will not shoot off to infinity and is therefore always bounded. There is also a more specific stability definition referred to as marginal stability, which pertains to a situation where the output shows bounded oscillatory behavior. It is obvious that a marginally stable system is by definition also a BIBO stable system. As you probably know, we can study the stability of linear systems through analyzing the position of their corresponding poles. For unstable systems, we either have one or more poles on the right-hand plane, or that we just have more than one pair of poles on the j-omega axis. For stable systems, all the poles lie within the left-hand plane, and the marginally stable systems have exactly one pair of poles on the j-omega axis, with the rest of their poles lying in the left-hand plane. So in this exercise, we will apply a step signal of 1 volt to the cube servo and analyze the stability of the position and velocity responses. It is worth mentioning that the stability of a system is an intrinsic characteristic and does not depend on the type of input that we are using. As long as the input has a finite value, a stable system is expected to respond within finite bounds. So after running the simulation, you can see the velocity response in scope number 1 and the position response in scope number 2. Next up is the proportional derivative control of angular position of the cube servo. PID, or proportional integral derivative controllers, are perhaps the most common control design used for linear systems and are adopted across a wide range of applications. In the time domain, the PID controller has this form, where Kp, Ki, and Kd are all non-negative gains and denote the coefficients for the proportional, integral, and derivative terms respectively. And the error term EFT is defined as the reference value minus the measured output. If we take the Laplace of this equation, we can derive the frequency domain expression for the PID controller. But what do each of these terms actually do? The proportional term acts on the present error of the system. So for example, if the measured output is smaller than the reference value, the error is positive, and therefore a positive signal will be applied to the system to increase the output. The integral term adds up the error over time and is useful for minimizing the cumulative effect of smaller but consistent errors that the proportional term cannot get rid of. Finally, we have the derivative term that does not act on the error but on the time derivative, or the rate of change of the error. What this term does is to basically penalize and drive the rate of change of the error to 0. Hence, this term helps make the response less aggressive, and it is often used to decrease the overshoot of the response. One other point to note about the derivative term is that it is susceptible to noisy error measurements. This is because differentiating a measured noisy signal will result in large fluctuations in the derivative signal. Finally, we have the block diagram of a PID controller in Simulink. First, the error is formed by subtracting the measured output from the reference signal RS. And this error is sent to 3 different paths to construct each of the P, I, and D terms. The proportional term is just a multiplication of the error and the proportional gain Kp. In the integral path, the error is multiplied by the integral gain Ki, and the integrator block is used to sum up the errors over time. And in the derivative path, the S transfer function acts as the derivative operator on the error, and then the resulting rate of change of error is multiplied by the derivative gain Kd. One question to ask is how these gain values are calculated. There are a number of ways through which we can design a PID controller. These include the Ziegler-Nichols and the root locus method. But here we're not going to discuss the control design in depth, and we'll focus more on the implementation. In this lab, we will use a variant of the PD controller to control the position of the servo motor. In a PD controller, the integral term of the standard PID formulation is neglected, and in the specific variant of the PD design that we use, namely the proportional velocity controller, the derivative term acts on the rate of change of the output instead of the rate of change of the error. You can verify this by looking at the time domain formulation of the control law, where the Kd term is multiplied by y dot instead of e dot. We can also derive the frequency domain representation of the controller by taking the Laplace of the above equation. And by substituting the frequency domain representation into the second order model for the cube servo, we can form the closed loop transfer function for the system. So this is the block diagram for the PD controller to control the position of the cube servo. The goal is to have the angular position of the cube servo follow a reference signal, which is a square wave with a amplitude of 0.5 and a frequency of 0.4 Hertz. We're using a PD design with a proportional gain of 2.5 and a derivative gain of 0.05. Here, there's one small modification to the PD controller that we discussed in the background section, and that is the inclusion of a low-pass filter before the derivative path. And that is to remove the fluctuations that may adversely affect the derivative control. So I'm going to run the simulation to see how the response looks like. In this plot, you can see the position response of the system subject to a step input for a proportional gain value of 2.5 and a derivative gain of 0.05. Next, I'm going to set the derivative gain to 0 and change the value of the proportional gain between 1 and 4. In the case where the proportional gain is set to 1, this is the output of the position response. And this is how the position response looks like with a gain value of 4. Next up, I'm going to change the proportional gain back to 2.5 and have a derivative gain of 0.15. We've also seen the response for the same proportional gain and a derivative gain of 0.05. We now want to see how increasing the derivative gain will affect the response of our system. And that's all for lab 4. Thanks for watching and goodbye.